Yeah.
Okay. So we were looking at applying differential equations for first order differential equations to problems. The the, the classic first example is just exponential growth, and the idea is that the rate of change of the population is proportional to the population at that time. So if you think about how much it grows at any time interval here, it's actually growing much faster, and it depends on how much you have at that moment. And there's like feedback, because as soon as you grow more, there's more population, and then in the next time step, it's just going to grow even faster, and then you're contributing more population, and so they're just feedback back and forth. But the fundamental physics is modeled by this statement here that says that the rate of change of the population is proportional to P, and you usually write that as an equation saying the derivative is the dP over dt is equal to some proportionality constant K times P. And this differential equation is a very simple differential equation to solve, because you can just use what we've learned before, where you can say that this is equivalent to a homogeneous equation. So if you just move you have dP over dt, and then do subtract kp. The only difference here is that our x is now p. Then you just have 0. So really, this statement is just this homogeneous equation. And so we know that the solution to this is P of t is equal to C e to the, it's going to be the negative of what's in front of this capital P, kt. So that's going to be the solution to this differential equation that just models that your rate of change is proportional to the population at that time. And suppose you also have some kind of initial condition. So I'll say your initial condition might be like, okay, at initial P, what is this? So your initial P, so P at time 0, let's say that's just like P naught. Then if you plug this initial condition in, this is like saying at T equals 0, you have P naught. So your population is this whenever your T is 0. So it's going to be C e to the K times 0, which just is the same as P naught is equal to C, because e raised to the 0 is just 1. And so that gives us that, suppose you have an initial condition where the initial population is P naught, then your C has to equal P naught. And so from this general model, this just means that this right here will be P naught. So your overall solution for when you have an initial population given to you will be initial population times C e k t. This is a model that you may have seen before. A lot other versions of this might have instead of a K, might have an R, and then people call this like PERT. So this is where it comes from. It's coming from this differential equation that states that the rate of change of a population growth at a given time is just proportional to your population at that time. And that's just describing the spirit of exponential growth. It comes from this idea. So we could do, a bunch of problems using this model that are probably not that new for some of you. So assume you have a fish in a lake that's the population is increasing exponentially with some constant growth rate K. The population is 1,000 in the year 2010, and the population increases to 3,000 in the year 2017. So if the exponential growth continues, what will be the population in 2040? So there's going to be, this is the model that we're going to have. So we'll just copy and paste this model. And we're just going to start with initial population looks like it's 1,000 in the year 2010. So we'll just measure time from 2010. So I'll just say here, your 2010 will correspond to t equals 0. You have a population of 1,000. So automatically, that means that your P naught here is 1,000. So, I mean, you could solve for it by just plugging in this initial condition, right? This is just saying that P of 0 is equal to 1,000. So if you just plug that into here, it's like saying 1,000 here, T is 0, E raised to 0 is 1. So P naught must equal 1,000. And then this model still isn't going to be fully complete without also determining K. K is like the growth rate. And how do we determine the growth rate comes from using another piece of data that they give us, which is that it increases to 3,000 in the year 2017. So 2017 is t equals 7. So if you're using 2010 as t equals 0, and at that point you have a population of 3,000. So you can plug that into this model. If you do that, then you have like 3,000 is the population at, we know the initial is 1,000, so I'll use that, e to the k times 7. And it's probably small, but that's e to the k times 7. And so if you just divide everything by 1,000, it's just going to become 3 is equal to e to the 7k. And then you can solve for k by just taking the ln. The ln and the e cancels, so you have this. So therefore your k, your growth rate, given the information they provide, is this. And this is the k that will go into here. So I'll just say that this k is really ln of 3 over 7. So we have the full model now. We have the model, the complete model that is going to be that is going to allow us to be able to find what the fish population is in 2040. So our full model is just P of t is equal to 1,000 e to the kt. So k is equal to ln of 3. So it's just going to be like, I'll just write it this way, t ln of 3 over 7. This is after you multiply the t by ln of 3 over 7. And then what they're asking for is just find the population at 2040. That's going to correspond to t equals 30. So what does this mean? This statement here saying find the fish population at 2040. Well, 2040, if you're measuring 2010 as t equals 0, then this is just asking for this. And so we'll just find that by just plugging in 30 into the t. So it'll be 1,000 e to the 30 times ln of 3 over 7. And this you'll just have to do on your calculator. And this is actually, this is how many fish there would be, assuming exponential growth, which is probably not a good thing to assume because Fish will probably die in the process as well. So it's not like all the fish that initially was living in 2010 continues to live at 2040. This assumption is just thinking that they're just multiplying constantly and just modeling a population and not accounting for fish dying. And also there's usually like a limit to how much an ecosystem can sustain, a population of fish. There's probably limited nutrients and stuff. So there's going to be, of course, that's going to be another source of death because some fish are not going to be able to get all the resources they need to survive. But this is just assuming if you had exponential growth in the population. There are differential equations that will account for things like dying and so-called carrying capacity of your environment. So there might be a limit to how much resources there are that can sustain a population, and those would introduce additional terms in your differential equation. So you have Kp here on the right-hand side, but there may be other terms that will account for those other complications. And yeah, maybe I might do that as we move on forward, but we're just going to look at just this simple case and apply it to different situations. And then maybe we can go back and look at additional complications to this. So this is probably not realistic, but this is what it is. Another place where we use exponential growth is in banking and finance. Like if you put money in some kind of account, they generally pay interest on it. That is going to be a function of how much money there is at that time. And so you're going to have some rate of change of your money in your account that is proportional to how much money you have at that moment, which is kind of like the population growth, except for instead of population, it's like of fish, it's of money. And so you're going to be, that's the idea of compounding continuously, is the thing that you're just, the rate of change of your money is going to depend on how much money there is at that moment in your account. And that's going to add money to your account, and there's feedback back and forth. And so it's going to compound on top of the money that additional money that you earned through interest, and it just continuously grows. And so in this case, the growth rate K is called the interest rate. And so you will have the same model, that uses this solution is coming from the differential equation we saw before, which is this is equal to the proportionality constant times P. So this was the fundamental idea, is that like your rate of change of, in this case, P is representing money, is going to be proportional to how much money you have at that moment. And the solution to this, because it's a homogeneous equation, if you move this over to the other side, or if you did separation of variables, will be this, and then the K is your interest rate. And so you might ask, you given this model, what is the interest earned after 1 year? What does that mean? That's like saying, how much money did you have after 1 year minus how much money did you have at the beginning? So this is what this is asking. So you could just say that you just are interested in computing this. So let's just do this minus P naught. And P of 1 using this model, just say P of 1 would equal P of 0 times e to the k times 1, which you don't have to write. So this will be P to the 0 times e to the k. This is exactly what this term is, minus what you had initially. And you could factor this e of 0 and just have ek minus 1. So that's how much interest you earn after 1 year. And then the question is, what fraction of the initial amount of money invested, which is called the principal. So I'll just say that this is actually money invested, which is called the principal. This is the initial money that you invested, is the initial amount that's in the account. P of 0 is earned in interest after 1 year. So that is like saying, let's just take the interest you earned after 1 year divided by the principal. What fraction of the initial amount invested is earned in interest? So this is the interest earned, and then fraction of the initial amount invested. So this will be like the principal. So this statement, what fraction, I'll just say, what fraction of the initial amount invested is earned in interest after 1 year? This is the fraction they're asking, which you can do very easily because we already found that this is really this. Just earned after 1 year is this. So we'll just copy and paste this on the top. And then you also have the principal, which is this. And I'll just use colors. And the P of P naughts cancel. So you just have that the fraction of the principal that you've earned in interest after 1 year is just this, which I'll just say is, no, not use red. Okay. And they have a name for this. They call this the effective interest rate or the yield. I mean, these are just almost just algebra because the differential equation is just solving this gets this. And then we're just doing whatever they tell us to do, like just compute the interest after 1 year using this model, and then compute this fraction using this model. So, but these have like these are where these things come from. Let's do, after defining all of these, let's do a problem that uses this. So suppose your money compounds continuously with an annual interest rate. So I guess I didn't say annual interest rate, but if it says 3% per year means that's an annual interest rate. What is your yield, which is called the effective interest rate after 1 year? We already said that the yield is this, so I'll just copy and paste this down here. This is our yield, given the definition we just saw on the previous page. So this is our yield, and they're giving us everything we need because they're saying that the interest rate is 3% per year, which means that that's K. You want to use it in decimal form, so this is actually the same as 0.03. So that's all you're going to plug in there. So you just have E times the 0.03 goes into the K. And then you do -1. And of course, this one, you have to use your calculator as well, because and it's going to become 0.004. So the effective interest rate for yield is, if you convert into percent, is 0.034%. Okay. So it looks different than the K, which is, this is called the annual interest rate. It's just the growth rate that's being your exponential growth model. But your effective interest rate, which is like how much interest you earned as a proportion of how much money you initially invested, is actually going to be always a little bit higher. And that's because of compounding. So say higher than the K is equal to 3% due to compounding. So your effective interest rate is a little bit higher just because of compounding, even though the model uses, so this is just called the growth rate, really is what the model uses, but the actual amount that you get out of it is actually higher because of compounding interest. Then you might also ask, how long does it take for the money to double? Okay, so you're starting with the original model that we have, which is P is equal to P naught e to the KT. But the time it takes to double is like saying, I want this final amount to be whatever initial amount we had, P naught, but twice it. So this is the idea of doubling, okay? And we're going to find the time it takes for this to happen. So this means that we have 2P naught is equal to P naught is EKT. You could divide both sides by the P naught, so you just get 2 is equal to EKT. And then you can just solve for T, which is the time it takes. So it's just going to be ln of 2 is equal to KT. Therefore, your T, I'll put a subscript D to say this is the doubling time, is equal to ln of 2 divided by your K. This is your doubling time. So for the, say, problem that we have here, the time it takes to double would just be TD is equal to ln of 2. Of course, our K is 0.03, so that goes into here. And so the time it takes to double is, if you type this in your calculator, 23.1. And what do you think are the units for the time to double? Yes. Yes, years. It takes a while. But that years is coming from the fact that you can see that there's really only units of year in our problem. And so these are probably not that bad because it's really just algebra. It's not really, the differential equations part was just this, the very beginning, where I just motivated that you might think of rate of growth as something that's proportional to the amount that you have at any given instant. And then in the next time step, there's going to be even more, and then it's just going to compound on top of each other. But this differential equation is just a simple first order linear homogeneous differential equation that actually has this solution. If you just read off the coefficient in front of this P, it's negative K, it's just K. We know this. And all we're doing is just using that for various problems that you may have seen before. But this is something else that I wanted to add to make things more interesting. What if you, not only have continuously compounding interest, but you also are making deposits and withdrawals into your account? But that's actually going to have like a complicated relationship, because as soon as you add more money into your account, then there's more money that your bank is going to compound. There's more interest that's going to compound. If you take money away, then you're going to lose out on some of the compounding. And so you want to be careful about like how those two will interact with each other. So we're going to use the language of differential equations to come up with the right equation that will model this scenario that includes deposits and withdrawals into your account. So because it's differential equations, it's really about rate of change, the derivatives. So this rate of change of money. So what is this? This is like dp over dt, where p is your money, but dp over dt. This is rate of change of money. Rate of increase due to interest. Do you remember what that term would look like? So it's like proportional to the amount of money you currently have. This is like let's not even have this. Just thinking about it as your rate of change is just from your interest. KP. Yeah, it's KP. So it's like rate of change due to interest. Interest is always going to be the amount that of increase is going, the interest is going to cause a rate of increase in your money that is proportional to the amount of money you have in that account. So what does that mean? That means the rate of change of money, dp over dt, equals kp, where k is your proportionality constant and p is your current amount of money, right? It always goes back to this model that we saw before here, this saying that the amount of money that rate of change of money is going to equal the rate of change due to interest is going to be KP because it's proportional to how much money you have at the time, which is the capital P. So that term, that first term isn't new. We're just adding this additional term right here, rate of increase due to deposits. So let's just on the side say that you have no interest. Okay, let's look at them individually, separately. So let's say you have no interest and you deposit $100 per year. If you have no interest and you're just depositing $100 per year, your rate of change of money, right? So let's use units for this. So you'll say that DP is in dollars, and let's say that this is in years, DT is in years. If you're say there's no interest, so there's no KP, but you just deposit $100 in that year, your DP over DT is equal to what? How much is your change in money over the year if you're only depositing 100? Yes. It's actually just 100. The change, yeah, it's the change in the amount that you're actually experiencing will just be 100. So DP over DT is like your change in money over the year, and you're just depositing 100. So that means your DP over DT is just 100. Say no interest and you just deposit. I mean, this is a very simple differential equation. You just take the antiderivative. So your P of T will equal 100T plus some integration constant C. And so does this make sense? This makes sense because it just says that if your money is modeled by capital P and you're depositing $100 per year, again, this T is measured in years, then after 1 year, it would just be like 100 times 1 plus the C. What do you think the C would be? The initial amount in your account. Yeah. So let's say you have, for instance, P naught is equal to some initial amount, P sub 0. Then this is like P sub 0 is equal to 100 times 0 plus C. So C is really your initial amount. But this differential equation will give you this solution, which is consistent with the claim that, with the statement that every year you're going to be increasing by 100. Because after 1 year, it'll be like 1 times 100 plus the initial amount C. After 2 years, it would be 2 times 100. And so this is just a linear growth, which is not very great because if you want your money to grow faster than this, then you don't want it to be linear, you want it to be exponential. But so you may have both happening at the same time. Suppose you're putting in money at the rate of $100 per year while it's also compounding. Then you'll have your DP over DT equals your interest rate of increase due to interest, which is the KP term, plus, well, suppose if we had 100 as the amount that you're depositing per year, it'll be plus 100 right here. Right? So if you think about how much the rate of change of your money, there's going to be something due to interest, which is proportional to how much money you have at the time, plus some fixed amount that you're just putting in every year. That's like your 100. And so you now have a differential equation that's a little bit more, it has just an additional term. So I'll just say most banks compound daily, but so this continuous compounding is not exactly what they do, but it's going to be a good approximation for when you have daily compounding. So if you just had continuous compounding, we know from before that this model is given by this. But if you have additional deposits that are being made, then you're going to have an additional term right here. So why don't we have a situation where you invest P naught dollars is invested at an annual interest rate of K. That's compounded daily, but we're going to use, we're going to assume continuous compounding as a good approximation for that. And suppose you make a deposit or withdrawal of B dollars N times a year. So this looked like I just, did one contribution of $100 over the year. But what if you split that across, like, let's say you make a contribution like every month, and the amount that you contribute every month is B dollars. So then your differential equation will look like this. It would be dP over dt equals the part due to interest, which is going to be Kp, where K is the proportional outcomes and P is the current amount of dollars. Plus, instead of 100, I'm just saying that I'm going to make a deposit or withdrawal of N dollars, B dollars N times a year. So it'll be N times B. And the B could be negative. So this could have been negative 100 if we're interested in withdrawing money. So this is the differential equation. It's different from this blue box. This is from before. The one we had before only had a term due to the interest. But now we're going to have another term here, NB, which is modeling that you're putting in B dollars N times a year. So this is the differential equation describing the rate of change of money for this situation. So I'll underline this in green and put this around box around this. So this is the new differential equation. The P is the only variable in, well, T is also a variable too, but P is your unknown. K is a constant, N is a constant, and B is a constant, because we're assuming that we know how much money that we're putting in B, and then how many times we're doing it. So if it's like a monthly deposit of $10 times N, that would be, you'll have 10 for B, and then if it's monthly, then N would be 12 over the year. Let's solve this differential equation. We're probably not going to get P equals CE to the KT. We're going to get something more complicated because now we have this additional term right here. It's actually not a homogeneous equation anymore, because if you write this in standard form, you're going to just, what does it mean to standard form? It means all your unknown, which is your capital P, I shove to the one side. So the only term I'm going to move to the left is the KP term, because this P is like our X. This NB term is like a constant. So in the past, when we didn't have this NB, it was just a homogeneous equation, and we could just read off the solution, right? That's what we had up here, where we had just dP equals Kp. Put the Kp to the other side. There's only a 0 here, and this is just homogeneous, so you can just see the solution right away. This one has got a non-homogeneous, so this right-hand side is not 0. So, but we know how to solve. So a couple things, these are all constants at the end of the day. So I'll just say that this K is a constant, right? Because we're assuming like the interest rate doesn't change. And then this is all just a constant. So I'll call this a constant forcing, right? Because both N and B are constants. It's the known amount that you're going to contribute, how many times you're going to plan on contributing over the year. So when you have constant forcing or constant input, your particular solution, which is P of P, I guess, because your unknown is P and particular solution P, is going to be a constant, capital A. And then we're going to plug that in. The derivative of constant is 0, so I'll just write 0, minus, you're going to have K times the A. And we're saying that has to equal NB, which means that our A is equal to negative NB over K. Using the method of undetermined coefficients, just a constant input. And so we have our solution because we know the particular solution, and we now can read off the homogeneous solution. So the particular solution is just this. And I'll use purple. Plus the homogeneous solution is just reading off what this would have been as CE to the KT. And this is, so I'll just say that this is your particular solution. Let's just move this down. And this is technically like our homogeneous solution, so I'll just use pH. And so suppose we want to use the initial condition they give us. So they say, suppose the amount of P naught dollars is invested. So the initial investment, let's just say that we have P of 0 is equal to P naught. That's just, if you plug it in, would be like P naught is equal to negative NBK times C e to the k times 0. And if you solve for C, this is like C times 1. So you can just, just say C is equal to P naught plus the NB over K. So you're just going to add this NBK to the side. So that goes into this C right here. So our official model, if we apply the initial condition, is going to be equal to the negative NB over K plus this C, P naught plus NB over K times the e to the KT. Okay. So this is the full model that will describe how your money is going to evolve as a function of time with annual interest rate of K compounded daily, which you're going to assume is compounded continuously, is this good approximation, with some fixed amount of deposits and withdrawals of n times a year. This is much harder than, so what did we have before? Before we had this differential equation, and that differential equation ended up giving you the P of T is equal to C, or I guess with the initial condition, P naught e to the KT. So this is what we had before. This was if you had no deposits or withdrawals being made throughout the year. It was just this. But if you are going to put money into it or withdraw money out of it, then the model becomes this. And it's just more complicated because there's like money you're putting in or taking out that is also going to get wrapped into how much compounding that's going to happen on it. And so it's not like there's like some kind of interaction that's going on at every instant. You put money, there's now more money that's going to compound on it. So you really want to build the differential equation like this, which is just saying that my rate of change is now going to have two contributions, one from interest, which is proportional to how much money I have at the time. That's why it has a P term, plus some constant. This one doesn't have any dependence on the amount of money you have at the time because it's just some fixed amount you're putting in. And it doesn't care, that rate of increase doesn't care about how much money you have in the account at that time. It's just a fixed amount that you're putting in. And those two are your two contributions to your money. And that's the rate of change. But then you want to use your stuff that we've learned in the past to solve this differential equation. Turns out that it's a non-homogeneous first order linear differential equation. It has constant coefficient, assuming that the annual interest rate K doesn't change. I mean, if it does, then you'll have to use the integrating factor, but we're going to assume that it's fixed annual interest rate. Then it's just a method of undetermined coefficients can be used because you just have a constant forcing function on the right-hand side. There are some caveats. So, of course, this interest rate model, this thing that's in this blue box, which is the first term here, is assuming that you have continuous compounding. So this assumes continuous compounding. In practice, your bank might compound monthly or compound semi-annually or whatever. If it doesn't do that, if it does that, then this isn't going to be a good model. This will probably overestimate how much money you have in your account, but it would be a good model for daily compounding, which I think most of the time they do. Continuous compounding just means that it's compounding at every instant. So the closer you can get to that, the better this model will be. If you're compounding semi-annually or quarterly or something, then this is going to overestimate the amount of compounding that you have. So this assumes continuous compounding because of this differential equation. And it's going to be a good approximation for daily compounding. If you had like quarterly or monthly, then you probably need you need a discrete model, So, discrete differential equations is not, we're going to work continuous in our class. And so the limit for the modeling that we can do in this situation is continuous compounding because we're going to assume continuous models. The other thing is, why am I getting a call? Just stop this thing. The other thing that I wanted to mention is that people you might ask, okay, if I'm contributing, let's say we said we're contributing $100, and it does matter when you contribute the $100 into your bank account, right? So like if you put the $100 at the beginning of the year, like in January, and then you look at how much money you have in December, you're going to have more than if you just added the $100 later in your year, because the earlier you introduce that deposit, it's going to compound on that. And so it does actually matter when you distribute the $100 over the year. But this model is going to assume that you actually just are depositing, like say the $100 continuously over the entire year. So if you think about this, what's the graph for this P of T? You just have some C, which is your initial, I guess say P naught, which is your initial amount. And then it's just going to have a slope of 100. So I'll just say M is equal to 100. I mean, it's basically like Y equals MX plus B. M is 100 and C is like your Y-intercept. And so this is like a continuous model that assumes that you are depositing money constantly at every second, and it's got this, so it's not realistic, I think. Really what you would be probably doing is you'd be like depositing money in a discrete way. You're probably going to be depositing money like this. Of course, if you're just putting in money like every day or something like that, then it'll be kind of like a step function. But this model is assuming that you're just putting in money, trickling in money like continuously, which is going to be a good approximation for if you were just putting in money like every day or something like that. It's going to be weird if you end up putting a huge amount of money at the beginning and then no money later. Or if you like don't put money in at all and then suddenly put in a lot of money at the end. So these are some limitations to this. So I'll just say here, this model actually also assumes continuous deposits. So I guess it would best model daily deposits, just like it would best model daily compounding. So that's the thing, is just like if you were thinking about like the subtlety about this model and its limitation, it's kind of an idealized model that looks at this kind of situation. So let's maybe at least do like maybe part A of this. Suppose you have a $10,000 is invested at 12% annual interest. Okay, so this one's so easy that you probably could do the other one too, because we have a couple minutes. How much money will you have in the account after 10 years? This is just, you're not putting in additional money or withdrawing additional money. You're just putting in this initial amount, 100,000, and then there's an annual interest rate of that. So you really just need to use this model for this case. It's just interest. So it's going to be dP over dt equals kp. And we already know that this solution is P of t is equal to your initial amount of money times e to the kt. And so we just are interested in how much there is at 10 years from now. So that's going to be like, you have the initial, which is 10,000 times e. Your annual interest rate is 12, so it's going to be 0.12 times the 10, which is, if you type in your calculator, approximately 3201.17. So it's growing, well, it takes 10 years to do this, but you're like more than tripling the money after 10 years. It's probably a really good annual interest rate because it's 12%. Yeah, it's very good. Now, let's just build the equation for part B. Suppose you make additional investment of $1 every day. How much money will you have after 10 years? So same 10 years, one without adding any money to it. The other, you're just like, I'm just skipping. Well, coffee doesn't cost $1, but like, let's say it does. Then it's like, I'm skipping coffee every day and just putting that money in to the account. After 10 years, how much of a difference that would make? Your differential equation will be different. It'll be dp over dt is going to equal your kp, which is going to be your 0.12, because that's your annual interest rate, times p, plus what's the additional term here? It's going to be the 365, because there's 365 days in a year, times the $1 you're contributing. And so you'll have this differential equation, dp over dt is equal to, or minus 0.12p is equal to 365. This is like a non-homogeneous differential equation that you can use your particular solution and solve for the p in this case. And it'll probably be a much bigger number than this because you're contributing money, and that money is also getting interest added to it. And so we'll do that next time. But these are different equations because one has just interest, the other one has money you're putting in as a function. If you're withdrawing, then it's negative. And so instead of like, plus 365 times C, yeah, that's where we'll do that next time. Yeah, we'll do like how much would happen if you were withdrawing $1 a day. And yes, yes.
So Harrison